Welcome back. In this video, we continue with chapter 0 and we move to section 0.3 about vector spaces. Understanding vector spaces is very important, especially infinite dimensional vector spaces is very important in functional analysis. Okay, because most of the interesting spaces of functional analysis are infinite dimensional. So we have to revisit this important notion and introduce the notion of algebraic basis in order to understand better why the spaces of functional analysis are mainly infinite dimensional. Okay, and we will be also applying Zorn's lemma to prove the existence of the basis. Okay. So to simplify the discussion, we'll always consider real vector spaces. And now let us give a general definition of a basis and dimension. Okay, because in linear algebra of first year, you mainly studied finite dimensional spaces, so it was a little bit restrictive. But many concepts of linear algebra can be extended to any dimension. So if we have a vector space over R and a subset B of E, which can be written as a collection of elements, EI, so this is reminiscent of the notion for a basis, actually. So a linear combination of elements of B is any finite sum of the form alpha I, E. So I multiply each EI by a real number and do the summation, and the summation is finite. Because here we don't have any topology on the vector space, so we cannot talk about convergence of infinite series. Okay? So when we talk about sums should be finite, because we don't know how to do an infinite sum without the notion of convergence. Okay, so a linear combination is actually what you call a finite linear combination in first year. Okay, so this is easy. The set of all linear combinations of elements of B is denoted by span of B or vect B, and it's called the space spanned by B. And it's easy to prove that span B is really a subspace of E. Okay? And it's the smallest subspace containing B. Now, when B is just one element, is a singleton, then we can write span B by R to the RE, which is actually what? It's the space of multiples of E. Okay, so it's the form of all elements of the form T times E, where T is a real number. So this is a one-dimensional vector space, so it can be identified with a line. Okay, and as I said, the span of B, we can prove that span B is the smallest subspace of E containing B. And we say that B generates E if span B equal E. So what does this mean? This means that every element of E is a linear combination of elements of B. Okay? Okay, linear independence. So this is an extension of the notion of linear independence that you studied in first year, but for finite sets. Okay, but here, if I have an infinite set B, what does it mean to say that it's linearly independent? This means precisely that any finite subset of B is linearly independent. And if you want to rewrite this condition, it means that if a linear combination of elements of B, or of any finite elements of B, is 0, then all the coefficients are 0. Okay, so here again, we have to deal with finite sums. Of course, we can write this as an infinite sum, so we can write this as sum of alpha I, I in capital I, but only finitely many indices are not 0. Okay, so most of the indices are 0. So this is just another way of writing a finite sum. So it's an infinite sum with most coefficients 0. Okay, now we can prove that a set is linearly independent if and only if no element of the set is a linear combination of the other elements of B. And this is probably proved best in linear algebra. It's very easy. So it means that when I remove an element x from B, the x cannot belong to the span of B without x. Okay. Now, an algebraic basis, or also called Hamel basis of a vector space, is a linearly independent subset B of E that generates E. So two things, linearly independent and generates the whole space. So this is what we call a basis. Okay. And what do we mean by saying that a vector space is finite dimensional or infinite dimensional? Finite dimension means that it's generated by a finite set. So this is what you studied in first year. So a vector space is infinite dimensional if it cannot be generated by a finite set. Now, as you proved probably in linear algebra that any finite dimension space is a finite basis, not totally trivial, but we shall prove something more general. We shall prove that any vector space has a basis, not necessarily finite. Okay? But if you restrict yourself to finite dimension spaces, then all bases have the same number of elements, and this same number of elements is called the dimension of the space. Okay? And it's denoted by dim of E. Okay, and you also proved that if a vector space has dimension n, then any set containing more than n elements is necessarily linearly dependent. So one element is a linear combination of the others. Okay, I'm not going to prove this. So as a corollary, if a space has an infinite linearly independent set, as we shall give an example now, then the space is infinite dimensional. Or equivalently, if you can find sets, arbitrary large sets, which are linearly independent, then the space is infinite dimensional. For example, if for every integer m, you can find a linearly independent set of size m, so finite, then the space is infinite dimensional. It's the same thing. Okay. So now I'll give an example. Why the space of continuous functions from 0, 1 to r is infinite dimensional. We know that it's a vector space. This can be confusing, actually, because when I ask this question to students, some say it's 1, some say it's 2, some don't know, but it's actually infinite. Why? Because it's enough to consider the space of polynomials, which is smaller. If you consider just the monomials, so f0 equal 1, f1 equal x to the 1, f2 of x is x squared, and so on. So we have now a sequence of functions, a sequence of monomials. If we denote this set by B, so B is now an infinite set, actually, I claim that it's linearly independent according to our definition. Okay, what does it mean to say that B is linearly independent? It's equivalent to say that any finite subset of B is linearly independent. This is the definition, because here we cannot deal with infinite sums. So, okay, now consider a finite subset of B. Okay, then this set is necessarily contained in the set f0, f1, etc. up to fm. Could be something smaller. Okay, so m, if you like, is an upper bound of the number of elements of B. Okay. So if I prove that this bigger set is linearly independent, then the smaller set is linearly independent as well, as you know. Okay? If the big one is linearly independent, the smaller one is linearly independent as well. Now, why this set is linearly independent? This set has m plus 1 elements. Okay, so consider a zero linear combination of this set. Okay, we have to prove that all the coefficients are 0. So now don't confuse alpha k with fk, because alpha k is a real number, whereas fk is a function, which is a monomial. This is a linear combination of functions, and it's 0. What does it mean that it's 0? It means that it's 0 at every point. So it means that alpha 0 plus alpha 1x plus etc. up to alpha mxm is 0 for every x on the interval 0, 1. So we have a polynomial here now, which is identically 0. And you know that a polynomial is identically 0 if and only if all its coefficients are 0. And there are several ways to prove this. You may use Taylor's formula, because if you denote this by p of x, then you see that alpha k is the case derivative at 0 of divided by k factorial. So if p is identically 0, then all the derivatives are 0, and therefore all the coefficients are 0. Or we can, another way to see this is that a non-zero polynomial has finitely many roots, okay? Or at most finitely many roots in R. But here, this polynomial has infinitely many roots, right? So it cannot be non-zero. So all the coefficients must be 0. And therefore, the set f0, f1, f up to fm is linearly independent, and therefore, every finite subset of B is linearly independent, and therefore B is linearly independent. Therefore, this space is infinite dimensional according to our definition. So we cannot find a finite basis of it. Okay. Now, question, what is span of B? What is the vector space generated by B, by this set? It's not C01, it's something smaller. I want you to think of this. What is span of B? Okay, and now, as an application of Zor's lemma, we shall prove that every vector space has an algebraic basis, and possibly infinite. Okay, so consider the collection calligraphic A of all linearly independent subsets of the vector space under consideration that I call E. Okay, so this is a collection or a set of sets, if you like. Now, this collection is not empty because the empty set is in the collection, right? Because the empty set is linearly independent. And non-zero singletons are also linearly independent. If you take just one non-zero element, it's linearly independent. Okay? We assume that E is not reduced to one element, because actually, what is the basis of if E is just 0, what is the basis of E? This is an extreme particular case. If E is reduced to 1 to the origin, okay, so it's 0-dimensional. What is a basis of E? It's the empty set, okay, by convention. Okay, now, so we can disregard this extreme case because it's not interesting. So we order this collection of all linearly independent subsets of E by inclusion. So we get an ordered set. As you may guess, we will prove that A has a maximal element. Okay, how do I prove that? I must prove that it's inductive. Okay, how do I prove that it's inductive? I consider a chain of A, which is just a totally ordered subset of A. So any two elements of calligraphic M are comparable. So now M is a collection of subsets. So I can write M as the collection Bi, I in some index set. This is convenient. And I claim now that the union of all these sets is linearly independent. Okay, how do I prove that? I go back to the definition. So I consider a finite, so I have to prove that any finite set of this union is linearly independent. So take n elements, E1 up to En, in the union, and consider a zero linear combination of these elements. I want to prove that all the coefficients must vanish. Not terribly difficult. Now, for each k between 1 and n, ek is in the union. So ek is in one of them, is one of the Bi. So there is an index ik, not necessarily unique, such that ek is in Bi. So E1, for example, is in Bi1, E2 is in Bi2, could be the same, we don't care. So each ek is in bik. Okay. Now we use the assumption that M is totally ordered. If M is totally ordered, it means that any two elements of M are comparable under inclusion. So for every I and j in the index set, either bi is contained in bj or the other way around. So this collection now, so I have now a finite collection, bi1, bi2 up to bin. Since this collection is totally ordered, there is the maximum element, right? Because I can compare any two of them and I can take the maximum. Okay, not difficult to see. So call this biggest set with respect to inclusion BIL. Okay, BIL contains all the others. Therefore, all these vectors E1 up to En are in the same set BIL because they are in BIK. So they are both in BIL. But recall that every BI is a subset of M and therefore a subset of A. So it's linearly independent, right? So we have now n vectors in a linearly independent set, and we have a zero linear combination. So therefore, all the coefficients must vanish because BIL is linearly independent, and therefore any subset of BIL is linearly independent. So this proves that the union of BI is linearly independent. Okay, and therefore this set belongs to the collection calligraphic A. And we are almost done because now for every I, the set BI is contained in the union. Therefore, this element in A is an upper bound of M because any element of M is bounded from above by this union. And that's it. So this means that calligraphic A is inductive. And that's it. So now we are ready to apply Zorn's lemma. So that tells me that A has a maximal element, right? And I call it B. And now it's enough to prove that B generates E because then B would be linearly independent and generates the space, so it's a basis, and that's it. So we can think of a basis as being a maximal linearly independent set. So this is another way of proving that a set is a basis. So maximal, it means it cannot be extended to a bigger linearly independent set. Okay, so we reason by contradiction. If B does not generate E, then there exists an element in E which is not a linear combination of elements of B, so it's not in the span of B. And therefore, according to what we said before, B union X is linearly independent. Okay, this equivalent actually. But this contradicts the maximality of B because B is now contained in a strictly bigger linear independent set. So we get a contradiction, and therefore B generates C. And that's it. So this proves the proposition. And more generally, we have what we call the incomplete basis theorem. If you have a linearly independent subset B of vector space E, then we can add to B elements so that to obtain a basis. Okay? So actually, the previous theorem was a particular case, but it's the same proof. In the previous theorem, we just took, we start with the empty set and obtain a basis. Here, we can start with any set, linearly independent set, and add to it elements. You probably encountered this in linear algebra, but in the finite dimensional situation. So, but here it's more general. So if you start with any linear independent subset, if it's a basis, it's okay, you do nothing. If it's not a basis, I can add elements until I get a basis. Okay, so same proof actually, but here, instead of considering the collection of all linearly independent subsets of E, we consider the collection of all linearly independent subsets of E that contains B. Okay, and we just use the same arguments. So we prove that B is inductive, therefore it has a maximal element, and therefore we are done. Okay, so this is important actually. Okay, now I move to the notion of algebraic complements and quotient spaces that you probably encountered in some course on algebra. But this is important. So if you have two subspaces f and g of a vector space E, we say that E is the direct sum of f and g, and we write E equal f plus g if, as you know, two conditions hold. The intersection of f and g is the origin, and every element of E can be split as the sum of two elements, one in f and one in g. And of course, when these two conditions are satisfied, this composition is unique. This decomposition is unique. And the map that to each x associates the x1 is the projection onto f, and the other one is the projection onto g. And in this case, we say that G is an algebraic complement of F. Okay, so note that in this section, there's no topology, just pure algebra. And according to what we said, actually, every subspace of a vector space has an algebraic complement. Why this is true? Because of the previous result. So if we take any subspace F of E, so as we know, F has a basis according to theorem 0.5. So take a basis B of F. And now complete this basis. So B is linearly independent. So it's not a basis of E, but we can augment it to obtain a basis B prime of E. And therefore, if I take G to be the span of the difference between B prime and so what I added here, then it's easily shown that E is the direct sum of F. So G is the complement. Actually, the algebraic complement is not unique, but two algebraic complements are isomorphic, actually, as you may know. So, and as I said, the decomposition is unique when we have a direct sum. So we have two projections now. Okay, and as I said, two algebraic complements of the same subspace are isomorphic, and their common dimension is called the codimension of the space F. So the codimension could be infinity, right? Because, okay, so, and you probably proved that all these complements actually are isomorphic to what we call the quotient space of E by F, which is the space of equivalence classes by this relation. So the equivalence relation between two elements is that the difference must belong to F. So this is an equivalence relation, and therefore the quotient space of this relation is denoted by E over F. And you usually prove in algebra that any complement, any algebraic complement of F is isomorphic in the sense of algebraic isomorphism, because there's no topology here. So just isomorphism is just linear bijection. Okay. So I'm not going to prove that. You can do it if you like. There's no harm in it. And what is the vector space structure that you can put on the set is the usual one, the obvious one. The sum of two equivalence classes, the class of the sum, and same thing for. So this makes E over F as a vector space, and that's it. Now I will end this video with some review on convexity, which is very important and we shall encounter later. Okay, so convexity can be just defined in the context of vector spaces. We don't need topology. Okay, so when a subset of a vector space is convex, it's convex if any convex combination of elements of A is in A. So actually, this is what we call, this is a particular case of a linear combination of X and Y, but the coefficients must belong to 0 and 1. So this is what we may call convex combination. Okay, and you can generalize this to a finite sum, not just two terms. Okay, so a convex combination is just a linear combination, but the coefficients must belong to 0, 1. Here we have just two elements, so the elements must be of the form T and 1 minus T because they sum to 1. Okay, and this is, by the way, so the set of elements of this form is called the straight line segment joining X to Y. So the geometric interpretation of convexity is any straight line segment joining 2 points of A is an A. So this is convexity. can draw a figure. And now, just for notation, because we shall use it later, if you have two subsets A and B of a vector space and alpha is a real number, we can define the sum of two sets in the usual way. So the sum of two sets is the set of sums of elements. So A plus B is the set of elements x plus y, where x is in A and y is in B, and alpha A is the set of multiples by alpha of elements of A. So these are the sum of two sets and multiple of a set. And we can observe that A plus B is the image of the product of A and B, the Cartesian product, under the map that to each couple xy associate the sum. This is important actually in order to understand later properties of compactness and so on. So these two, this set and this set, the first set is the image under a linear map, not bilinear, linear in the product. Okay, and the second one is also the image under a linear map from E to E, which is just the homotopy. So the second set is just the homothetic of A of ratio alpha with respect to the origin. Okay, so this notation is very useful. And now I will combine these all these notions together by a proposition. So if A and B are subsets of a vector space E, then if A is convex, then A plus A is 2A. Now, this is not trivial at all, because there is a difference between A plus, so it's not because we are not adding numbers here, we are adding sets. So there's a difference. A plus A is the set of all elements of the form x plus y, where x is in A and y is in A. But there's no reason why y should be equal to x. However, the set 2A is the set of elements of the form 2x. Okay? So of course, 2A is contained in A plus A, because 2A, because if an element is here, it's x plus x, so it's here. But the converse, the reverse inclusion is true under the assumption that A is convex. Try to prove that, actually. It's not difficult, straightforward. So this is not trivial. And actually, the converse of this is true. If A plus A is 2A, then A is convex. But we shall not need this. But you can do it as a difficult exercise. And it's easy to see that the image of a convex set under a linear map is also convex. So linearity conserves convexity. Straightforward. In particular, if I consider the homotopy alpha x, then if A is convex, then alpha A is convex as well. Then this is should be clear geometrically. And therefore, also, if A and B are convex, then their sum is also a convex set, because A plus B is the image of A times B, and A times B is convex, as you may check, actually. So if A is convex and B is convex, A times B is convex in E times E, so its image under the linear map is convex as well. Okay, so this concludes this video on vector spaces. In the next video, I'm going to cover norm spaces. So we shall put a topology on our vector spaces. So thank you for your attention and see you next time.